Okay, this is a video lecture for Math 181, Calculus 1. And this video lecture is for Thursday, April 9th. The topic today is optimization. What does optimization relate to? Basically, it's an application of the techniques we've been learning about maximizing or minimizing functions. So we apply this to some real-life situations, and I'll list three common applications of optimization. But there are many more applications than this. One application is in the business world. If you're a business, your goal is to minimize your costs and to maximize revenues. Another common application of optimization is to minimizing transportation time. Okay, let me let you guys see that. And then a third application I can think of is to maximizing areas and volumes. Okay, so the good news is the techniques we've learned already for finding the maximum minimum values of a function, we basically apply those techniques to some real life situations. And what I'm going to do is consider three real life examples of optimizing certain quantities. So let's get started. Okay, our first example relates to optimizing a fenced-in area, or maximizing. So these are our examples. Maximizing a fenced-in area. And the situation here is we have a house here, and we'd like to fence in a garden area. Okay. And this is our garden area here, so we're going to have fence along these dotted lines. And the given information is we have 160 feet of fencing. And we'd like to figure out the dimensions of this rectangular area that will maximize the area. Okay, so we want to maximize the amount of area fenced in. We have 160 feet of fence. So how do we do this? The first step here is labeling our diagram. And so I'm going to call this dimension x and y. This is also x. So we're going to label our dimensions there. And then we're going to try to write some equations that relate these dimensions to the length and the area. Okay, what is the length of our fencing? This is our fencing here. So our length L is equal to y plus x, right? Because this is our perimeter of fencing. And then this will equal y plus 2x, and we know that we have 160 feet of fencing. So that's our first equation. We have two variables here. So if we're going to solve for our two variables, we need to have two equations. Our second equation relates to the area. It's a simple equation. As you guys should know, the area of a rectangle is x times y. Okay, these are our two equations. And what I'm going to do is I'm going to solve this top one for y, and then plug it into our area equation. If I solve this for y, I get y equals 160 minus 2x. Okay, then I'm going to put this into our equation, our area equation. So that gives us this equation. Area equals x times 160 minus 2x. This is an equation for the area purely in terms of our dimension x. And then I'm going to distribute this, so we get 160x minus 2x squared. Okay, that's our area equation. Now the goal of this problem is we want to maximize the area. So to find the maximum values of any function, we always take a derivative and set equal to 0. So we're going to take the derivative of the area. We get dA dx, set this equal to 0, and then take our derivative. This comes out to 160 minus 4x. Okay, and then we solve this for x. If we solve it for x, we get 4x equals 160. And this means that x equals 40. Let's call this feet. Yeah, it's feet. This is 40 feet. Okay. And that means our y dimension here is 80 feet because y is equal to, well actually that's true, but let's show why that's true. So now we want to solve for y. We can use this equation right here. Y equals 160 minus 2 times x. X is 40. This equals 160 minus 80, which equals 80. Okay. So our dimensions are we have a 40 by 80 foot rectangular area enclosed. Okay. So this is a case where we found the dimensions of this piece of ground that maximize the area. We also might be curious about what is the maximum area. The maximum area, we know from above here, our area equals 160 times x. In this case, x is 40 minus 2 times 40 squared. And if you guys multiply this out, this should come out to 3,200 square feet. Let me just check that. That's correct. So these are the dimensions that maximize this rectangular piece of garden, and then this is the actual maximum area of that garden. Okay, this is a classic optimization problem. Let's do a couple more problems. There's really no new theory here. We've learned the theory already in this chapter. We're really just applying this to some real-life problems. The second problem I want to consider is a business application. Okay, let's consider a business application. And in this particular case, we have a baseball team, and they play in a certain stadium. And they find, the front office finds that when ticket prices are $10, when you have a price of $10, you have an attendance of 27,000. And we also find when the price is $8, there's an attendance of 33,000. So as what we'd expect, as you lower the ticket prices, the attendance here is more people come to the games, right? What we want to do in this case is we want to find the optimal ticket price. Find optimal price of ticket that maximizes revenue. If you're a business, if you're the owner of this team, you want to maximize revenue. You want to find the optimal ticket price that will maximize revenue. If your tickets are too expensive, no one's going to come. If your tickets are too cheap, a lot of people will come, but you're not getting much out of each ticket. You know, if you had a zero ticket price, you might get huge crowds, but you're not getting any money. If you had a $100 ticket price, yeah, you've got a great price per person, but you may not get anyone coming to your game. So there's some optimal price. Let's try to find that price. And as the first part of this problem, in the process of finding that price, what we're going to do is try to find an equation for the ticket price. Find an equation for ticket price as a function of the attendance. Okay, and in this case, I'm going to let the attendance be x. I'm going to call the attendance x. So x is the attendance at a particular game. Can I find an equation for the price as a function of a? I'm going to assume a linear model here. I'm going to assume that the ticket price and the attendance are linearly related. And since they're linear, what I can do is find this. So I have some relation. I'm going to have some relation. P of x equals mx plus b. Okay? I'm assuming a linear relationship between the ticket price and the attendance. So my goal here is to find the slope and the y-intercept. Let's find the slope. The slope here is the y values here. Let's use this given data here we've collected. So the y values are $10 minus $8. We're going to use our classic slope formula. Y2 minus y1 equals x2 minus x1. Downstairs, when I have a $10 ticket price, I have 27,000. When I have an $8 ticket price, I have 33,000. So this is what I get for my slope. This comes out to 2 divided by minus 6,000. And this comes out to minus 0.00033 repeating. Okay, and this is, what are the units of this? This is dollars per person. So there's a negative here because as ticket prices goes down, as ticket price goes down, the attendance goes up. So there's a negative linear relationship. This is my slope. I need to now find the y-intercept here, and let's do that. So what I do is I plug in, choose your favorite point here. Let's plug it in. I'll choose this point. So when I have a ticket price of 10, I have this slope I just found, 0.033 repeating, times an attendance of 27,000. Okay, and then I'm going to add on b. All right. I'll let you guys do the arithmetic here. If you solve for b in this equation, you get, let me check my notes. What do we get here? If we solve for b, we get 19. Okay, but I'll let you guys verify that. So this means that I can now write my ticket price as a function of my attendance, p of x equals minus 0.00033 repeating times the attendance x plus 19. Okay, that's my my ticket price. Let me talk about this a little bit. What if there's no attendance? What ticket price correlates to no attendance? Well, if you have no attendance, x is 0, and that means $19 is a ticket price that correlates to no attendance. What does this really mean? It means if you set the ticket price to $19, no one's going to show up because it's too expensive. Another interesting calculation is how many people will attend if the ticket price is 0. And to do that, we plug in 0 for our price. We get 0 equals minus 0.00033 repeating x plus 19. If we solve this for x, we get 57,000. So what this means is if you set the ticket price to 0, you'll get 57,000 people showing up, and not more than that. Maybe that's because there's only 57,000 people who even want to go to a baseball game, even if it were for free. If you set the ticket price to 19, no one will show up. So there's some ticket price between $0 and $19 that will maximize your revenue. You're not getting any revenue at $19. You're not getting any revenue at $0. There's some price in between those two that maximizes this revenue. Let's find that price. Okay, so I'm going to erase this here. Keep in mind this equation for our ticket price. Okay, let's write that equation for our ticket price down. This is P of X equals 19 minus 0.00033 repeating times X. This is the ticket price as a function of X. Now, I want to find the revenue. Let's say if we're a business person, we don't really care so much. We care about the price, but we really care about the revenue. Well, revenue is a simple relationship to price. If you open a lemonade stand and sell so many cups of lemonade at such a price, you multiply those two together to get the revenue. So the revenue will equal X times P of X. Basically equals the ticket price times how many people attend. Okay, and so I'm going to multiply this out and I get X times 19 minus 0.00033 repeating times X. And if we do this, we get 19x minus 0.00033 times x squared. So this is now our revenue. This is our revenue function. This is the revenue as a function of attendance for this baseball team. Now we want to find the revenue. We want to find the attendance that will maximize revenue. When you hear those words, maximize revenue, you should think take a derivative of the revenue and set equal to 0. That's exactly what we'll do. So we take the r, the x, okay? We set this equal to 0, and then we take the derivative of this right-hand side. If we do that, we get 19 minus 0.00066 repeating x, because we bring this 2 down. So now this is the derivative. This is the derivative of the revenue with respect to x. And now what we want to do is solve for x. So if we solve for x, we get minus 0.000 plus 0.0066, repeating x equals 19, and x then equals 19 divided by 0.00066, repeating, and this comes out to, if you plug this in your calculators, this comes out to 28,500. Okay, what is this? This is the attendance. This is the attendance that maximizes our revenue. Okay, this is the attendance that maximizes the revenue. What price does this attendance correspond to? Well, we can plug back in for the price. So price when the attendance equals 28,500 will be 19 minus 0.00033 repeating times 28,500. And I'll let you guys calculate that, but this comes out to 950. That comes out to 950. So it turns out, if you're the owner of this baseball team, you should set the ticket price to 950 because that will maximize your revenue. Now we could actually calculate what the revenue is. I won't do that right here. It's a simple calculation. But we know that we want to set the ticket price to 950, which makes sense because that's somewhere in between our ticket price of 0 and 19 where we get no revenue. In fact, this is exactly halfway between those two endpoints of no revenue. But this is good to know. If you were the owner, you would want to set the ticket price to 950. Okay, we're going to do a third optimization problem. I hope you guys are having fun with these. This is neat because it's a really great application of calculus to everyday life. Our third problem has to do with minimizing the production cost of a soda can. We want to minimize the production cost of a soda can. How do we do that? Well, let's first draw we'll assume this is like our standard, cylindrical soda can. So we'll draw this cylinder here. That's our soda can. We'll assume this is 12 ounces. Nowadays we have a lot bigger sodas out there too. 12 ounces happens to be 340.2 centimeters cubed. That's the volume of the soda can. And we would like to figure out what dimensions should this soda can have in order to maximize. I didn't explain this quite well. We want to minimize the production cost of the soda can. What that really means is we want to minimize the amount of metal we use to produce this soda can. We don't want to produce a lot of metal and have a small amount of soda. We want to minimize the amount of metal we use. So in other words, what this means is we want to maximize we want to minimize the surface area, minimize the amount of surface area of the soda can because the surface area has to do with how much metal we produce. So in other words, this really means we want to minimize the surface area of our can. We want to minimize the surface area of the can to minimize our production costs. Let's label the dimensions of this can. This is our height, and this is our radius, okay? And what we can do is start writing equations we might know for various things. Well, we have a volume here. This is the volume of our can. So I'm going to start by writing an equation for the volume of the cylinder. And it turns out the volume of a cylinder is pi r squared times h, right? It's the area of the base times the height is our volume of the soda can. Okay, and we know that this volume is equal to 300, we want this volume to be equal to 340.2 centimeters cubed. Okay, now let's see if we can write an equation for the surface area of our can. Okay, the surface area of our can is going to be made up of three parts. It's going to be made up of the base, the top, and then the side walls. Okay, well, the area of the base, the area of a circle, right, is pi r squared. Okay, the area of the top, you get another pi r squared. And then we want to find the area of the side walls. It turns out the area, if you think about this, the side wall has a height of h. Well, what's the perimeter? What's the length of this side wall? If we cut this side wall in two and made it out flat, what would be the length of that? The answers would be actually the circumference of this circle. So the area, the surface area of the sidewalls is 2 pi r, right? The circumference of our circle times the height, 2 pi r h. And now we can combine like terms. This comes out to 2 pi r squared plus 2 pi r h. That's our surface area. Okay. Now we want to minimize the surface area here. The problem is the surface area we have is a function of 2 variables, r and h, and that's a problem. We want to just have it as a function of 1 variable. But the way out of this is, what we can do as a strategy is we can solve this equation. So we have this equation here. We're going to solve it for, let me actually check what I do in my notes. Either r or h, we could do it either way. We're going to solve this for h, yeah. Let's solve this equation for h, and then I'm going to plug it into this equation to solve it for to minimize the surface area. So if I solve this equation for h, let's go back over to the volume. I know that h will equal 340.2 centimeters cubed divided by pi r squared. That's now my formula for h, and then I'm going to plug this formula into here. So now my surface area formula becomes 2 pi r squared plus 2 pi r times h, which is subbing in, I get 340.2 centimeters cubed divided by pi r squared. Okay, and some things are going to cancel out here. This simplifies to 2 pi r squared plus, we're going to cancel this r, we're going to cancel one of the powers of that r, the pi's cancel here, and we get a 2 multiplied upstairs, so this comes out to 680, right, 680.4 divided by r. Okay. This is our surface area equation. So what we've done is we've now written the surface area equation as a function of just one variable r. So that was a lot of work here. Let's just review what we did. We're minimizing the production cost of a soda can, which means minimizing the surface area of the soda can, minimizing the amount of metal involved. And what we've done is we've written equations for the volume and the surface area. But the surface area equation had 2 variables in it, so we used the volume equation to eliminate one of those variables. Now we have the surface area as a function of just one variable r. And now we want to minimize the surface area. Well, when you hear the word minimize, you should think, take a derivative of the surface area with respect to r and set equal to 0. That's exactly what we'll do. So we'll take the derivative of the surface area with respect to r. Okay, set that equal to 0. All right. And what this comes out to, if we take the derivative here, we get 4 pi r. We get 4 pi r. Okay, and then here, this term, we can think of it as 680.4. We can write this r as r to the minus 1. Okay, if we take the derivative of this function, we pull down the minus 1, we get a minus 1 in front. We get 680.4 divided by r to the minus 2, which is r squared downstairs. So if we take the derivative of this, we get minus 680.4 over r squared. Now what do we want to do here? We want to solve this for r. There's various ways we could do that. Let's see, I'm going to rewrite this equation. I'm going to bring one of these terms to the other side. So I get 4 pi r equals 680.4 over r squared. Okay, I'm running out of room, so why don't I erase this? We'll come back to this equation in a second. Okay, our equation is, if I remember this correctly, it was 4 pi r equals 680.4 over r squared, right? Let me just double check that, yes. And here's our soda can right here. Let's just draw this again so we can remind ourselves of the geometry of the situation. And now we want to solve this equation for r. Well, we could cross multiply. If we cross multiply, we get 4 pi r cubed equals 680.4. We're solving for r. That means r cubed equals 680.4 over 4 pi. Okay. We want to solve for r. We're going to take the cube root of both sides of this equation. Take the cube root. Okay. That leads us to r. The cube root of r cubed is just r. That means r is equal to the cube root of 680.4 over 4 pi. And if you guys plug this in your calculator, we get r comes out to 3.78 centimeters, believe it or not. So if we want to minimize the production cost of the soda can, we should make r equal to 3.78 centimeters. Now we also are interested in the height. What's the height? If this is r, right? If this is r, this is our height. What is the height? So we need to calculate the height. Well, fortunately, we earlier found an equation for the height. Let me bring this up again. Where is that equation? The height equals 340.2 divided by pi r squared. We found this equation earlier. So now we're going to plug in our value of r. And we have pi times r, which is 3.78 squared. And if we plug all this in, we get a height equal to 7.57 centimeters. Okay. 7.56 centimeters. Okay. And interestingly enough, this is our height. Interestingly enough, this equals exactly 2 times the radius. This is exactly 2 times the radius. So what this is telling us is if we want to minimize the production cost of the soda can, we want to make the height equal to 2 times the radius, or in other words, we want to make the height equal to the diameter. So our soda can should look something like, let me see if I can draw this correctly. Our soda can should look something like this, okay? Where this is our height, this is our diameter, and the height equals the diameter, okay? Now, you might think to yourself, well, when I buy a soda can in the store, that's not the shape of the soda can. And, you know, the soda can isn't exactly a perfect cylinder. It has a little cup at the bottom and so on. So there must be, I'm sure there are subtleties to that. But this is still an interesting problem. It's a first order look at minimizing the production cost of something. Okay, so those are 3 great examples of optimization, which is basically applying the techniques we've learned for maximizing or minimizing values of functions to real-world applications. And I will see you guys on Thursday.